Okay, so this is where I'm told that we got to at the end of the last lecture. So that should ring a few bells. Yeah, happy with that? Yeah, okay. So we've looked at linear circuits so far, and we're going to start looking at nonlinear circuits, but we can also put nonlinear elements in the feedback loop and still have a circuit we can analyze with our linear theory, bizarrely. But so we're going to look at this then. So if we make the transfer function, which is the relationship between the output and the input, vary in amplitude with frequency, for example, make it amplitude dependent, we can have a non-linear circuit. And there's all kinds of interesting things we might want to do with that. Compression, expansion functions. The old Dolby system was this kind of system where you can sort of compress things and expand things and do a bit of little encoding. So let's put something weird in the feedback loop. And we're still doing negative feedback, so we've still got a negative feedback amplifier in this. But we've complicated the issue a bit by replacing the resistor that we would normally have here with a diode. And as you can see by the heading on the slide, it's proposed that this is a logarithmic amplifier. So it turns the output into the logarithm of the input. Okay. So to analyze this, we can apply exactly the same sort of techniques. Okay, we can apply the virtual theorem, and we have to say that whatever the current is going through here must be the current going through the outside, because the input impedance of the op-amp is very, very high and no current goes in. And Kirchhoff's laws say that what goes in must come out of the node. So we've broken it into two little chunks. We've got a current going through here, and we've got the same current going through here. And then we just need to look at both ends of the circuit and see what's going on. Now, I think you should be familiar with this. Do we recognize this equation here? You can't see over there. This is the diode equation. Yeah, some people are nodding. That means you all know, just some of you have forgotten. So this is the relationship between the voltage and the current in that diode. It comes from semiconductor physics. It's a simplified version. And the current through the diode is given by some sort of constancy thing, the reverse saturation current, as it turns out, multiplied by some exponential that's related to V, the voltage across the diode. And these are constants-ish. Okay? Charge of electron, Boltzmann's constant, and absolute temperature, or temperature in kelvins. Obviously temperature may not be constant, but we'll assume it is. And then there's a -1 to give us what happens in the reverse direction. So IS becomes that. Reverse saturation current becomes -IS. So as we only ever use diodes in the forward direction in this kind of circuit here, we can forget this -1, and we end up with this. So we've got an exponential relating the voltage to the current. Okay? And we know that we've got V out at one end of the diode, and we know that the other end is at 0 because of the virtual ground. So we can work out that this is what's going on at the diode end of things. That's the voltage difference across the diode, 0 minus V out. Okay, there's no significance in the difference between little v and big V in this case. It's just PowerPoint doing its thing. And the input current is very much straightforward. It's V in over R, because one end of the resistor is at 0 because of the virtual ground. And both currents are the same. So we can say that I equals V in equals ISE to the minus Q, the exponential bit. And we can get rid of the I at that point then. And then if we just take the logs of both sides, so the log of the exponential just gives us the in the exponential bit, and then the log of the input side. And we can rearrange that to give us V out is equal to some notional constant, slightly dependent on temperature, multiplied by the log of some scaling factor, because these are fixed, times V in. So output is proportional to the log of V in. So we can start to make quite complicated mathematical functions with these virtual grounds and feedback loops if we wanted to. So this was the basis of analog computing, where you can build a circuit that does calculations for you. Some equation can be implemented within an analog circuit and it responds pretty instantly, quicker than a digital system. But unfortunately the output is dependent on the temperature of the diode, because we have a temperature relation, and also this IS, this saturation current, is also dependent on temperature. It only handles positive inputs, because if the voltage is negative, V in over here, then we reverse bias the diode, and that equation no longer, strictly speaking, applies. Okay, that's okay, because the log of a negative number doesn't really exist anyway. So these circuits are used to handle signals that have a large dynamic range, say 10 to the 5 to the 1. So you're going from, say, 1 microvolt to a volt in your input signal, and you want to be able to differentiate between those levels of signal. That's a big linear scale. If you do a log of it, then everything becomes in powers, and everything gets concertinaed down. And we do a bit more of that later when we start looking at Bode plots and frequency analysis. Has Paul done Bode plots with you? Yes.
Well, only labs actually, but not formally.
Okay, all right. But they're logarithmic scales, so you've got a log-log scale. Turns everything into straight lines. It's great. But we'll do that next week probably. Okay, so an optical scanner, for example, the amplifier in an optical scanner, things that scan your shopping, might well have some kind of logarithmic circuit in the front end, because the light reflecting off the barcode varies in intensity tremendously depending on how close you are to the scanner and what angle you are and all that kind of stuff. So a dynamic range of 10 to the 5 or something is something that's really useful there to try and get everything into a sensible range. We could also make a multiplier, because if we take the log of two numbers and then add them together and then do an anti-log, we've multiplied. That's the nature of logarithms. You certainly used to do that at school. Maybe you don't know. If you don't, you've learned something new. Logs can make multipliers by just adding. So you can do the log of two input numbers, add them in our adder, and then all we need is an anti-log amplifier to get the multiplication back. Dead easy. And this is the anti-log amplifier. Move the diode from here to here. See? A certain amount of common sense starts to apply when you understand these architectures. Give you some clues as to what's going on. So we're not going to analyse that. We don't need to go any further than that. You, armed with those equations and the knowledge of the virtual Earth theorem, should be able to figure this one out. So another interesting application of feedback loops with nonlinear elements in there is something called a precision diode. So diodes are very good, but they have this issue, if you like, that you need to sort of turn them on before they do their rectification. You need to put about 0.6, 0.7 of a volt across a diode before it starts to really turn on. And sometimes that's a problem, particularly with small signals, less than about 0.7 of a volt. Diode won't even see them. Okay, and rectification, which is effectively what we want to do with these things, is a common thing that we want to do. And so what we can do with rectification is we take a sine wave, peak amplitude of A, its average is going to be 0, because its peak is plus and minus A, so the average of a sine wave is 0. So that's difficult. If you want to find out what's going on in terms of any changes of amplitude in here, because the average is still 0, you need to rectify it, which basically means chop off the bottom half of the signal. Okay, so that's called half wave rectified, because all we've done is just chop off the negative part of this signal. Okay, so the peak amplitude is now A, the average is now bigger than naught, the average of that waveform. something complicated, but it's bigger than naught. So that will go up and down with the average amplitude of this. And we can do something called full wave rectification, where we take the bottom half of our sine wave and we flip it up. So now we've got that. And it's more sensitive to sort of demodulation and stuff. And we can take an average of that, and you can get this DC level go up and down as we change the amplitude of that. This is really good for communications for amplitude demodulation. Okay. We can achieve rectification with the diode, because it blocks in one direction and allows current in the other direction. But we have to overcome this fact that the diode needs about 0.6 of a volt across it before it turns on. So if we were to plot this equation here and put the sensible numbers in for a proper diode, we would end up with that. Okay, so it goes through 0, 0, and then it rises exponentially. Although it's so small, you can't see it. However, if we'd plotted this on a logarithmic scale, you'd have seen it. But we haven't, because of the scale. So this is actually rising exponentially, although you can't see it, because it's very small. And then the exponential starts to take off. And it really goes for it. It doesn't take very long before the gradient of this is super steep. Which effectively means it's got zero resistance, because the gradient is equal to the resistance, or 1 over the gradient. So this is why people say that about 0.6 of a volt is the turn-on voltage for a diode, because below that, it might be doing its exponential thing, but you can't see it. Above that, it happens really quickly. So 0.6, 0.7, depending on who you talk to and what's the chemistry of your diode. That's when it comes on. But what it means is that any signal that's occurring in this region, below about 0.6, diode isn't really going to respond to. Just going to stop it. Right, so if our signal, for example, is huge with respect to 0.6 of a volt, it doesn't really matter. So here's a signal, here's a little circuit, so we've got a sine wave, 240 volt signal coming in here, big signal. We've got a diode and a resistor. So this is a sort of a amplitude-dependent potential divider. So in one direction, this is going to allow current to go through, and the voltage seen here will be the voltage seen here. And the other direction, it's going to block it, and then you're going to get no volts here. So if you put that into your simulator and run it through with a 50 hertz signal, for example, you can see that it's getting pretty close, 60, 40, 20, 0 volts here. Looks pretty much like 0, and it goes all the way up to 240. So we've taken our sine wave and we've rectified it, halfway rectified it. It's got rid of the bottom half of the signal. That's what's happened here. And that's great. But if we start putting in small signals, it's a bit different. Okay. So here we're putting in signals of 0.1 of a volt, 0.3 of a volt, 0.5, 0.7, 1, and 2 volts. And I'll leave it for you to work out which is which. There's a certain logic applied to it. And what we can see is that at very low voltages, signal voltages coming in, 0.1 of a volt, we're not seeing anything. Probably not. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's 0 buried in here. It's not even registering. And it's when we get up to 0.71 or 2 volts that this is starting to do its rectification. And look, you've lost a lot of the width of the signal. This should be, how wide should it be? That wide. For the full sine wave rectification. But we're not getting anywhere near that. Even with a 2 volt signal, we're losing a little bit of our signal. And look, it's only going up to 1.4 volts on the scale. 1.4 volts is the peak of this, but we're putting in a 2 volt signal. And that's because we've lost 0.6 of a volt across our diode because it's turned on. So we've got 2 volts here, 0.6 dropped across the diode, so we're only going to see 1.4 here, tops, for a 2 volt signal. That's a big percentage of the signal gone. Put 240 volts in, it's not an issue. You lose 0.6 of a volt and 240, you're not going to notice, are you? They're both electrocuted quite happily. This, a bit more different. So, we'd like to be able to do something about this, because it's quite common to have small signals, particularly from like radio transmitters and stuff, that we want to rectify because they're amplitude modulated or whatever. We want to demodulate them. But if we put a diode in the feedback loop of an op-amp, then all of a sudden we're getting up to 2 volts for a 2 volt input, and we're getting the full width of the sine wave. We're getting perfect rectification. We haven't lost anything, we haven't got any distortion or anything like that. And look, it's gone all the way down. So we've got 0.2, 1.4, 1, 0.7. They're all going down, all the way down to, this is 0.1, the red line. We're still rectifying it really well, and we're not losing, as far as we can see, anything at the corners. We've made a perfect diode with 0 turn-on voltage because of the wonderfulness of this virtual earth and the op-amp having a very, very high internal gain. So the op-amp maintains its inputs at 0, because that's what op-amps do with no negative feedback, which means it provides an output voltage to just turn the diode on for no input at all. So it's adjusting its voltage here to give us our 0.6 volt drop across here, which then becomes, this is plus 0.6, this becomes 0, comes back, and we've got 0 between the two. So it's adjusted its output to give us this little offset, ready to move really fast, ready to respond to any signal that comes in. All right. So there's a discussion, for those of you who wish to follow it through. If we consider an input signal, say 1 volt into the op-amp, we've got 1 volt coming in. Okay. It's going to try and maintain the difference between these two as 0. So it's going to try and make this one 1 volt if it can. All it can do is adjust its output. But because this is always going to be about 0.6 below, if this is on, then this voltage has to go higher to give us 0.6 across here, to give us 1 volt there. So the op-amp is doing a balancing trick for you. It's doing all the hard work. Okay. So it's always sitting, the output of the op-amp here is always sitting at this point here, ready to turn on really fast. Yeah, you can zoom in and have a look. It's not quite perfect because the op-amp doesn't have an infinite gain, but you know, much better than the diode on its own. Right, it's not perfect because when the input goes negative, no current flows through the diode. Here's our diode. The input goes negative, then it tries to make this go negative to drop that, but it can't pull current through the diode because the diode blocks it. So we've ended up with an open circuit system at that point. It's not linear anymore. It's like it's open circuit at that point if the input goes negative, which means it doesn't matter what happens at this output here, op-amp can do what it likes. It's not going to affect the input. We're not connected anymore. Okay? So what that's going to mean is it's going to try really, really hard to adjust its output to maintain its inputs at 0, but it's never going to get there. So what's going to happen is it's going to throw this output to the supply rail, because that's as far as it can go. Still have no input on this, because this is now non-linear, because there's no feedback connection, because the diode's in the way. And that means that when the input then goes positive, and this circuit becomes forward biased and operating again, this point here, which is sitting at the supply rail, suddenly has to move really, really fast to get down to the point to maintain these at 0. It's got to go down to close to 0. And it can't move its output infinitely fast. That's something called a slew rate. It takes time to recover. So what you find in a basic circuit like this, if you look at the op-amp output, which is this bit rather than this bit, you find that it goes very negative, and then you can see the time it takes to recover itself before it can then start to do its rectification. So there's a little bit of distortion at the edges. Okay? But you have to start looking quite closely to see this for low speed signals. High speed signals, it starts to become important because this time becomes a significant fraction of your waveform. A certain number of degrees at high frequency. Right, so that's the key. It becomes open circuit when, i.e. no feedback, when the input goes negative because of the nature of the diode. So there's a bit of, even though this is wonderful when you look at it in a global scale, macro scale if you like, when you start going in to see what's really going on, you see that there's actually some little issues going on in here, and the op-amp is good, it's not brilliant, and these little sort of delays at the corners here that you have to zoom in to see might start to become significant. Okay, so that gives you a frequency limit effectively. So people then say, how can I improve this? This is just an example of how these things can go. So people then say, well, actually, what I need to do is stop the output going completely negative to the supply rail when the input goes negative. So they stick in another diode, or another resistor or whatever. And what that does is when it's negative, it clamps the output movement, can only go to minus 0.6, which is a long way away from the supply rail. So it hasn't got to come back very far. Only got to come back 0.6 to a volt now. You can do that very quickly. So if you want to analyze this, you've got to sort of break the circuit into two chunks. You've got to say, what does this circuit look like for positive inputs? Which of these diodes are open circuit? Which ones we're going to treat as short circuit? Redraw the circuit, analyze it. And then say, what does the circuit look like for negative inputs? Which diodes are on? Which diodes are off? Redraw the circuit, analyze it under those conditions, add the two together with superposition, if you like, but time-dependent superposition. Because you can't have both cases at once. Input is either negative or positive, can't be both at the same time. And so you can build up this part of the circuit, and then this part of the circuit, and add them together. So that's how you can analyze these circuits. Okay? So you can see that even with op-amps, there are some deficiencies, and a little bit of thought and knowledge of understanding what's going on allows you to sort of add extra components in to solve a particular problem, to improve the performance of some circuit. Okay? So you're probably not going to understand this completely in the whizzing through that I've done, but this is what engineers have to do. They would spend a lot of time designing this circuit to make it work. It's not something you can just write down. And if you want to make a precision full wave rectifier, so that the input waveform is the black line, and we actually get out the black and the red signal with no distortion at the edges and perfection. This is one implementation of a precision full wave rectifier using a couple of precision diodes and some adding circuits. And it looks quite complicated, and it is. But you can analyze this in exactly the same way. You can say which diodes are on for a positive circuit, which diodes are on for a negative input circuit, redraw the circuit in both cases, analyze it with the virtual earth theorem and the linear theory, add the two together in terms of time, and you'll get the response out. That's quite complicated, isn't it? Yeah. A bit baffling. All right. But if you do break it into chunks and know how to analyze it and just do it a step at a time, you'll get there. Now you just imagine the person who actually invented this circuit, came up with it. You know, how much knowledge he must have had. Or it was just a happy accident, which a lot of things are. Just randomly throw circuits together and hope for the best. And oh, look, it's a rectifier. And then analyze it, and then work out where you can improve it, maybe. I don't know. Okay, so that's the sort of thing you do in the third year on my analog module there. So if that scares you, don't do the third year module. If you're interested in that, the third year module may be for you. Okay, positive feedback circuits. So although the op-amp was designed to be used in a negative feedback configuration, and it gives us all these wonderful amplifier configurations and topologies that are dead easy to analyze, and also then dead easy to make complicated, we can use them in a positive feedback configuration as what's called or similar to a comparator. Op-amps and comparators are very similar. Comparators are designed to operate in positive circuit feedbacks, but you can use an op-amp if you really want to. So the basic idea of a positive feedback circuit is to try and use this instability that the positive feedback introduces. So if we were to wire up our non-inverting amplifier wrong, we get the input terminals run the wrong way, we'd end up with this, which happens a lot in the labs. And what you've then made is something called a Schmidt trigger, presumably named after Mr. Schmidt. I triggered him. And what this does is it gets rid of the negative feedback, because we're actually feeding back now to the positive input. That's positive feedback. Now, negative feedback acts to try and stabilize things and keep things the same. That's what negative feedback tries to do. Remember, when we had negative feedback, it was trying to keep the difference between these two zero with whatever's going on. Now, because of the way this has been fed back, everything goes the wrong way. So it'll look at this and it will say, I want to try and minimize the input difference here. All I can do is move my output. The output is now moving the wrong way. And so it gets worse, and it sees a bigger difference, and it says, oh, I need more compensation. It moves the output even further. This makes this difference even bigger. It tries even harder, and so on, until this goes to one or other of the supply rails and sits there looking at you. Can't go any further. And it gets there really, really fast, because of the gain in here being like 100,000 or more. And that's basically it. And it will compare the two inputs. If this input gets close to this input, then it might well try and flip its output. And if that happens, you'll find that this goes the other way, to the negative row. So it will actually compare the two inputs and say it's higher or it's lower. And there's not much in between. So if you want to compare something to a fixed reference voltage, that's what happens. So this is what's going on here. We're actually taking a sample of the output voltage with this potential divider. Let's call it 50%. These two resistors are the same, so we've got half the voltage here that we started off here, divided it in two. Presents that voltage here, no current goes in, infinite impedance. And so effectively, that's a reference level. The reference level is half the output voltage. This is 10 volts, this reference level is 5 volts. So it's looking at 5 volts here. And so it's comparing V in with 5 volts. Once V in gets close to 5 volts and goes the right way to flip the output, it flips the output and says it's gone the other way. And what that actually means is then this output will head towards, I don't know, minus 10 volts, because that's the other supply rail. This voltage will become minus 5 volts, because it's half the output voltage. And now the voltage being compared to the reference pin is minus 5 volts. So that's suddenly moved from plus 5 to minus 5. Which is probably a very long way away from this one, because this one's just triggered it at plus 5. So this one's round about plus 5, this one's now gone to minus 5, and that's waiting for that V in to move down to the next level to trigger it. So it's sort of a variable reference that this thing has created. All right. So the circuit will drive the output either to plus VCC or minus VCC, as the supply voltages. And you can see what's going on here. As I said, we've got a potential divider there. So that will be the input to V plus. Either plus or minus VCC multiplied by that potential divider. And the only point of interest is when V in gets close to whatever value this happens to be on the reference pin. And then the magic happens. All right. So I've explained what's going on. It's trying to maintain the difference of the inputs to zero. All it can do is adjust its output voltage one way or the other. If you connect it to the positive input, it can't adjust it the right way to minimize it. It can only adjust it to make it worse. And it just keeps making it worse until you get into the supply rail. Because of this. The same op-amp equation applies. As V plus gets bigger, V out gets bigger. This is the difference between the two. If the difference is huge, multiplied by a huge number, it tries to make V out huge, and it can only go to either supply or the negative supply. And that's it, really. And that's another way of saying the same thing, but stepping you through the various levels we get. So we're getting a bit digital here, because their output is high or low. Yeah. see what's going on there. So why is this good? Because if the V in is, say, a digital signal, a square wave coming in, and it's come a long way under the Atlantic, say, and is now a bit noisy and a bit small in level, it's a bit noisy, you want to get that square wave back again. You want to get rid of that noise. So what you can do is feed it into one of these Schmitt triggers, and when it's high with the noise on it, it'll switch the output high, and the high will just stay there and ignore the noise for now, because the noise isn't getting anywhere near the threshold anymore. And then when the square wave goes down with the noise on it, it'll trigger this level shift again, and you'll get the other level out. So you'll end up with a replication of the square wave that's coming in, but without the noise. So not filtering it as such, you're regenerating it. You're completely making a complete new copy of it without all the noisy stuff. Quite often used a lot as well for debouncing switches. If you push a switch button, it makes contact, and you expect the signal to go high or low or whatever and sit there. But because of the mechanics of switches, you can get something called switch bounce, where you ping it, and there's all springs in there, and the actual contact itself will bounce up and down a few times. And this will give you variation in your output, which might then trigger your digital circuits to do the same thing multiple times. This kind of circuit will stop that happening, because it'll just take the first level and then sit there. Okay, so that's the useful things of this. So you can draw this in a sort of a hysteresis diagram, show you what's going on. So we've got V in here, going out that way, which is interesting there, and we've got the output voltage, and the output voltage can either be high or low, plus VCC or minus VCC. So as V in starts negative, the output will be high, and as you increase the input, nothing much happens. Output stays high, output stays high, output stays high, output stays high, until you get to the trigger level, and then the output will flip. And if you keep going positive on your input, it just stays flipped. Yeah? And then if you start to come negative on your input voltage down here, it won't follow that path, because the reference level has moved. It'll follow this path until you get to the negative trigger point, and it will flip that way. So it will stay flipped until you exceed one or other. So you've got this sort of no man's land in the middle, which is sort of the protection zone. And by controlling the value of the resistors, R1 and R2, the values of that, you can change the width of this window. So you've got control over it.
This is that they really refer to the hysteresis diagram? Or?
That's a hysteresis diagram, yeah. Right, so debouncing switches, fine. Regenerating square waves, a bit more commercial, fine. But then some clever people thought, well, actually, if we make this time dependent as well, we can make something called an oscillator, which is a really useful circuit to have. So here's our Schmitt trigger, this bit at the bottom, which is our non-inverting amplifier, wired up the wrong way around. And then the input signal is dependent on the value of the output signal, but delayed in time by a capacitor. This is an RC circuit. Okay? So if this goes high, for example, it will charge up this capacitor. And it will charge, so the voltage across the capacitor will start to rise. And it rises at a rate which is defined by this value and the values that R and C. It gives us a time constant. So you can calculate how long it takes for this thing voltage to rise up. And of course then, eventually, it will cross this threshold point. And that will flip the output. And then this will start to discharge until it meets the voltage the other way. And then it will flip. And then it will flip. And you make an oscillator. It goes forever. So the voltage on V minus here is an RC transient. And you can use standard techniques that we've discussed to work out what the voltage is at V minus. And you will find out it's that. If you think back to the RC work, time constants and transients that you've done with Neil White, Dan Spence, last semester's course, who thought there'd be a use for it? There you go. put it in here to work out what's going on. And then thus, with a little bit of playing around, you end up with t, the period of this waveform, how long it takes to go up and down again, being equal to 2rc log, there we go, logs again, 1 plus 2r1 over r2. So we've got complete control over the period of this oscillator's waveform, which is now output square wave, by playing around with these values. Yeah, there's a lot of freedom in those. There's not just one solution. You can have multiple solutions for this. Okay. Derivations homework. Give you something to do. If you start looking at what's going on here, you can see that this RC time constant is this big black waveform, the sawtooth waveform. That's the charge and discharge curve for a single capacitor with a resistor circuit. And you can see that when it hits one trigger level or the other trigger level, the output moves either high or low. So the output of this is this Vout, is this black square wave, which has a 50% duty cycle, so it's equally high and equally low, and the frequency of it is controlled by the value that we've put into these components here. So you can make an oscillator for driving a clock. Clocks drive digital circuits. All digital circuits, well, synchronous digital circuits require a clock. There's an easy way to make one. Isn't that interesting? And we can go further. If we fed the output of the Schmitt trigger, which is a square wave, remember, of our, sorry, not the Schmitt trigger, the oscillator, into an integrator, we can make a triangle wave. And triangle waves open up the door to all kinds of interesting systems like pulse width modulation, things like that. Because if we integrate a square wave, which is just two DC levels, if you integrate a DC level, a constant, you get that constant times time as the output, which is a rising level with respect to time. And so if we integrate our square wave here, we would end up with a rising ramp, a falling ramp, a rising ramp, a falling ramp. We made a triangle. All we need is an integrator and a bit of imagination. And that is a good place to stop for this time, because we need to now move on to frequency-dependent amplifiers, which allow us to look at filters, differentiators, integrators, all that kind of stuff. And suddenly we've got a whole wealth of mathematical functions available to us with op-amps to build all kinds of complicated systems without worrying about what's in the op-amp. We haven't worried about what's in the op-amp for weeks, days probably. If indeed we've ever worried about what's in the op-amp. Hands up if you've ever worried about what's in an op-amp. Very wise. Okay, so see you next time.